Okay, in this video we're going to be looking at the law of large numbers and um, how it will apply to probabilities, and then we're going to get into something called expected values. So as we look at the law of large numbers, let's kind of look at this little scenario we have here. So you toss a coin once, you cannot predict exactly how it will land on that first try. You know that there's a, theoretically there's a 50-50 chance, heads versus tails, but that's all you can state. There's a 50% probability of heads. Now, if you toss the coin 100 times, you still cannot predict precisely how many heads are going to occur. However, you can reasonably expect to get close to 50% heads, or heads 50% of the time. If you toss the coin 1,000 times, you can expect the proportion of heads to be even closer to 50%. So in general, the more times you toss that coin, the closer the percentage will be to exactly 50%. So as you increase those number of events or trials, the more closely it will get to what we expect it to be, or what we would expect to be theoretically, which is at 50%. So the idea that large number of events may show some pattern, even when individual events are unpredictable. Again, you do it you throw a coin one time, you can't predict where it's heads or tails. You just know it's going to be one or the other, and there's a 50-50 chance. But when you see some pattern, even when those single events are unpredictable, it's called the law of large numbers. Sometimes you'll hear the law of averages. So the law of large numbers, we just say consider an event A with the probability of A in a single trial. The law of large numbers holds that the following: for a large number of trials, the proportion in which A occurs will be close to the probability of A. So one way to think of that is the observed probability will get closer and closer to the theoretical probability. Also, the law of large number, the larger the number of trials, the closer the proportion will be. Now, key idea here is this law holds as long as each trial is independent of prior trials. So then an individual trial always has the same probability. Once you start throwing dependency in there, the game changes. But that's the idea of law of large numbers. As we increase the number of trials, the closer that proportion that we observe will get to the actual true probability or theoretical probability. Okay, so in this example here, suppose you toss a fair coin 10,000 times. Should you expect to get exactly 5,000 heads? Why or why not? And then what does the law of large numbers tell you about the results you're likely to get? Okay, now to expect that you will get exactly 5,000, we should not expect 5,000 exactly, because we can't predict that. But the proportion, so the proportion of heads will approach, that says approach, 0.05 as the number of trials increases. So that's what the law of large numbers will tell us about those results. But we should not expect 5,000. We just expect that proportion will start to get closer and closer to 50% as the number increases. Okay, the next one, speedy driver. Suppose a man who has a habit of driving fast has never had a speeding ticket, but that's the habit. What does it mean to say that the law of averages, or the law of large numbers, will catch up with him? Is it true? And explain. So, will the law of large numbers, what does it mean if the law of averages will catch up to him? A lot of people think, in terms of, this case, it means he is, and here's what people say, due for a speeding ticket. He hasn't got one, but it's been long enough, his luck's going to run out and he's due for a speeding ticket. That's what would kind of be meant when people say the law of averages will catch up with him. Is that true? Well, if tickets are random, so if tickets are random, it is not true. So if the tickets are randomly distributed, that's not true, because the probability of getting a speeding ticket is not dependent upon what's happened in the past. Each time you get in the car, it's a new adventure, and your probability of getting a speeding ticket is the same as it was in all of your previous examples. So you're not necessarily due for a speeding ticket. That probability is always the same. But there can be, various outcomes. So again, when people say, the law of averages will catch up with you sometime, or your luck's going to run out, that they're talking about, person being due for something, but in probability, it's never the case. So like if you get 8 heads in a row, they say, oh, you're due for a tails. Actually, it's not true. You're just as likely to get a heads on the next one as you are to get a tails. But in our minds, we feel that that's how it should be. So now we're going to look at this idea called expected value and its role with probability and law of large numbers. So let's look at this example with a company called Insure-All. It sells a special type of insurance that pays the policyholder $100,000 in the event that he or she has to quit a job because of serious illness. So you pay premiums, and then if something happens and it's medically documented, you have a serious illness, they give you $100,000 in the event that you have to quit your job because of that illness. Now, based on data from past claims, the relative frequency probability that a policyholder will make such a claim is 1 in 5,000. So that probability is 1 out of 500, or excuse me, 1 out of 500. So the question is, should the insurance company expect to earn a profit if it sells them for $250 each? And this is what expected value is going to help us find out, is, where's this profitability with the given probability that has been observed over time of 1 in 500 will make this claim. Now, if Insure-All only sells a few policy, the profit or loss is very unpredictable. For example, if you sell only 100 policies at $250, this will generate, so you take 100 times 250, you'll generate $25,000. Now, if none of the policyholders file a claim, then you make a good profit. You make a $25,000 profit. However, if even one person makes a claim of $100,000 and that claim goes through, then you'll face a huge loss based off of, only insuring or holding 100 policies. So it's very unpredictable. One policy can sway the whole thing. There. Now, if you contrast that, if Insure-All sells a large number of policies, the law of large numbers tells us that the proportion of policies for which claims must be paid should be very close to the 1 in 500 probability for a single policy. So, for example, if the company sells 1 million policies, now we have a huge number here, it should expect that the number of policyholders making the $100,000 claim will be close to, you take the million policies, times it by 1 over 500, and you get 2,000. So out of the million, you would expect about 2,000 claims to be paid over the course of that year. So you pay 2,000 claims, $100,000 a claim, that's $200 million. That's a huge expense. And so this isn't, when we look at this, that $200 is the average for each individual policy. So that what it basically says is you expect to pay $200 for every policy that you have. And so if you expect on average that you're going to be paying out $200 per policy, that's your expected value of payout for each policy. If you're selling those policies for $250 each, then you should expect to earn on average, take what you charge minus what you expect to lose for every policy, and you have a positive $50 per policy. So you expect to make $50 per policy, and if you have 1 million policies, 50 times a million, that's $50 million in profit. So yeah, you paid out $200 million in claims, but on average you made $50 per policy, so you came right side up about 50 million. So we call this average the expected value for each policy. Note that it is expected only if the company sells large number of policies. So the larger the number, the more accurate this will become. So as we now look at expected value in general, here's how we will find the expected value. And this example only applies to 2 cases or 2 events, but it can be expanded to many events. But the expected value is found by taking the value of the first event times its probability plus the value of a second event times its probability, and that would be for 2 events. And this continues on. If you have 3, you'd say plus the value of event 3 times its probability plus the value of event 4 times its probability, and so forth. So just think of it as, you know, the value, how much you gain or lose, times the probability that that event occurs, plus the next one, how much you gain or lose, times the probability, and so forth. And so we're going to look at some examples here. And so in this one, we're playing a game. We want to find the expected value for you, not for you know, whomever you're playing against. Would you expect to win or lose in 1 game, in 100 games? We kind of explain our answers here. So you're given 5-to-1 odds against tossing 3 heads with 3 coins, meaning that 5-to-1 odds, you win $5 if you succeed, you lose $5 if you fail. So first what we need to do is we need to find the probability of the event, and the event here is the probability that you toss 3 heads. So you get heads, heads, heads with 3 tosses. Okay, well that's going to be 1/2 for the first times a half times a half. These are all independent, so we can multiply them together. So that becomes 1/8. So the probability that we get all 3 heads on the 3 tosses is 1/8. The probability that it's not heads, heads, heads is just 1 minus 1/8, or 7/8. So that's the probability of the 2 different events. So the expected value, what we're going to do is we're going to take the value for event 1, so that's you gain $5, so positive $5 times the probability of 1/8. Plus the second event, you lose $1, so that's plus -1, so it's a loss of $1 times its probability, which is 7/8. That's where the case where you do not get heads, heads, heads. Okay, and those are our 2 events that we have. So this becomes 5 times 1/8 is 5/8, and that'll be minus 7/8, which is 2/8, or 1/4. I'm sorry, negative. And as a decimal, this is negative 0.25. So that would be a loss of 25 cents. Now, does that mean every game you expect to lose 25 cents? Well, no, we can't predict that, because in a game you can only lose at most $1. So we can't predict 1 game. However, in the long run, what we can expect in this game is you can expect to lose 25 cents on average for each game played in the long run. So this is if you play this game over and over and over again. But we can't predict it for 1 particular game. We can only predict for long periods of time. So that's where the law of large numbers comes into play. So that's a brief look at expected value. We'll continue in a part 2. Hopefully this is making a little bit of sense, and we'll give you more examples.